Hello friends, very good afternoon to all of you. Today topic is sampling of a bandpass signals. Okay, so before going to this topic, so what is meant by bandpass signal? What is the purpose of bandpass signal in the real-time applications? Here, in case of the sampling of a bandpass signal, the signal which is band limited to the FM hertz has to be sampled at least at a 2 FM samples per second if the analog signal is to be reconstructed. So that statement is given by the sampling theorem. Sampling theorem states that if you want to reconstruct the message signal from the sampled version of a signal, the sampling frequency must be twice that of the message signal frequency. In case of the bandpass signal, that is x of f is equal 0 for all frequencies outside the range f1 less than f less than f2. It means that the bandpass frequency band is present in the range of f1 and f2 having a center frequency fc. So this is nothing but bandpass filter. Here fc value is not equal to 0, but in case of the low pass filtering, the should be criteria is different. If you observe the low pass filter structure, it is nothing but like this: ideal low pass filter having a frequency minus fm and fm, center frequency 0. This is nothing but maybe hr of omega. It is nothing but in terms of f. In case of the low pass filter, the center frequency value is 0, but in case of the band pass filter, the center frequency is non-zero value. So for this class of signals, while there will be no aliasing even fs is greater than 2f2, there might be no aliasing even fs less than 2f2. It means that in case of the bandpass filter, if you observe the bandpass filter spectrum, it is a spectrum of the bandpass filter having a frequency f1 and frequency f2 having a center frequency fc. If suppose fs value is greater than 2f2, it means that it is above this band. In the above this band, the frequency value is equal to 0, so there is no aliasing effect. In case of the fs less than 2f2 also, no frequency is existing. That means there is no another spectrum is present in case of this. Therefore, in case of the bandpass filter, we have a no aliasing effect is occurred is fs greater than 2f2 as well as fs less than 2f2 cases. But the sampling of a bandpass filter produces a two drawbacks. That is nothing but the first one is nothing but the spectrum of the sample signal will have a spectral gaps. That means if we consider in case of the bandpass sampling, so in between 0 to f1, in between 0 to fn, there is no frequency. That means there is no information is present in between this. That means it is a wastage of the bandwidth. Therefore, in case of the sampling, in case of the spectrum of the sample signal, we have spectral gaps. If f2 is large, the sampling rate is also very large. So, and therefore, it leads to the practical limitations. That means the frequency f2 value is very high. Frequency f2 value is very high. The sampling frequency fs is greater than 2f time. That means if the f2 value is increases, obviously sampling frequency is also increased. As the sampling frequency is increases, we need to reconstruct the corresponding filter is also very large. If you want to reconstruct the filter, or if you need any filter for the purpose of the corresponding reconstruction, it is associated with the different types of components. Therefore, the complexity of the filter is also increases. So, in case of the bandpass signal, the signal can be represented in terms of in phase and quadrature components. Here, xi of t is equal to in phase component plus quadrature component. Therefore, x of t is equal to xi of t into cos 2 pi fct minus xq of t into sin 2pi. Here xi of t is nothing but in phase component. Here xq of t is nothing but quadrature component of the corresponding signal. The bandpass signal x of t whose maximum frequency or whose maximum bandwidth is 2 fm can be completely recovered, can be completely represented and recovered from its samples. It is sampled at a maximum rate of the the complete sentence means that in case of the bandpass signal, x of t is the maximum bandwidth of 2 fm. If you want to retrieve or if you want to sample the corresponding signal, the frequency must be twice that of the maximum bandwidth. So let us consider in this case the bandpass filter B is equal to f2 minus f1. Here f2 is nothing but maximum frequency, f1 is nothing but lower cutoff frequency, therefore 2 into fm or 2 into maximum frequency. Therefore here fs is equal to 1 by t, that means fs is equal to sampling interval, therefore we know that fs is equal to 2f2. Therefore sampling frequency fs is equal to 2 times of the maximum frequency divided by m, where m is equal to large integer, therefore fs is equal to m is large integer which can be represented, m is equal to, therefore here m is equal to f2 divided by bandwidth of the signal. Therefore fs is equal to 2 times of the maximum frequency divided by m. So we know that 2f2 divided by m is equal to f2 divided by p. f2 get cancelled, therefore we will get the maximum frequency. So from this statement fs is equal to 2b. That means sampling frequency in case of the band pass filter is equal to twice that of the corresponding bandwidth. Now just we will go through the spectral representation of the band pass filter. So here the band pass signal of a band with 2fm, the minimum maximum sampling rate is equal to the twice of the band, therefore fs is equal to 2 into bandwidth, therefore fs is equal to 2 into 2fm, therefore sampling frequency fs is equal to 4 times of that maximum frequency samples per second. So the spectrum of the band pass signal x of omega can be represented as xs of omega is equal 1 by t into summation n is equal minus infinity to infinity x of omega minus 2nb. Here this is the spectrum for the band pass signal, f1 and f2 are the frequencies, fc is the central frequency, as well as this is a frequency spectrum for sampled version of the signal. The original signal can be recovered by passing the x of t through the ideal band pass filter with pass band given by the f1 less than f2 less than f2. So as the frequency f2 is greater than 2f2, there will be no aliasing. If f2 fs is equal to 2b, the reconstruction is not here, aliasing is not possible. So that is just a brief introduction about the band pass signal in case of the sampling theorem considerations. So thank you for watching this video. If you are